Next, what I'd like to do is to use Newton's second law to solve some of the most fun circular motion problems. And we can start with the roller coaster problems. These are always fun, maybe a little bit more fun to ride, but at my age, it's actually more fun to do the problems than to ride the roller coasters. However, they're both fun, and let's try them right now. So the first problem is here's the dreaded loop-de-loop. And what we want to find out here is what is the minimum speed required to keep this thing from falling out of the loop? In other words, we don't even need any, if we're going at this speed, we won't need anything to hold these wheels on there. And usually there are extra things to hold these on there in case it does slow down too much. But what is the minimum speed required to keep this thing going in a circle? So, first step, always a free body diagram. Let's go ahead and draw a free body diagram right up here. And we have, at this point, we have the force of gravity. This is a mass M, by the way. This is mass M. So we've got the force of gravity, mg, pulling this thing down. Is that the only force acting on this thing? Well, there's also the force of the track on it. Which direction is that? Well, it should be, if it's going at least the minimum speed and a little bit more, the force of the track on it would also be called the normal force, and that would be pointing down this way. I'll use the little n again. So there are my two forces acting on that cart. What's the minimum speed necessary to keep that going around a circle of radius little r like that? Let's go ahead and set up our Newton's second law equation. Right here, we've got the net force centripetal equals MAC. Notice the subscripts always agree. I'm going to get a little bit more specific here. Now, both of these are pointing down, so I want to ask you, would those forces be negative or positive? You might be tempted to say negative, but remember with circular motion, we're always making towards the center of the circle positive. So these are both positive forces right there. So I'm just going to say N plus mg equals MAC. Getting even more specific, N plus mg equals M, and AC, the centripetal acceleration, may not be the overall acceleration if there's tangential acceleration, but at least the centripetal acceleration will be v squared over r. Now the question is, what is the minimum speed necessary to keep this going in a circle? Now, as this gets slower and slower and slower, less and less force is required to keep it going around the circle. In fact, my question to you is, when it's going the absolute slowest that it can possibly go, what is the value of the normal force? When it's going exactly as slow as it can go, the only force required to keep it going in that circle is the force of gravity when it's at its slowest. So, at the slowest point, and this is not generally true, but if it's going as slow as it possibly can, in this situation, n will go to 0 because it's going as slow as it can. If it's going any slower, n would be a negative number. What does that mean? Well, that might mean that there's some hooks or some rungs that have to hold this thing up. But it wouldn't actually be a normal force necessarily in that situation. But we're going to just go with, let's deal with the limiting case of where it's going as slow as it can and no other forces are needed besides mg to keep it in a circle. Well, that's very simple then. All we got to do is, we got this, looks like the mass apparently does not matter whatsoever. So what is the necessary speed? Oh, that's easy. You just take g times r, multiply both sides by r, gr equals v squared. Hence, the speed that you need is just the square root of gr. We'll keep that going in a circle. That was easy. Let's try this over here. Let's say we have a person of mass. Let's make them a different letter. Let's make it a capital M. They have mass big M, and that's the person now. We're not looking at the cart anymore. We're looking at the person. And the question that we're asking here is, as they go over this hump right there, what's their apparent weight if they're going over at some speed v? So for this problem, we're given the speed v. In other words, we know that. We've got v. They're giving us that. They're asking what the apparent weight is of this person going over the top of this hill. Now, apparent weight is a somewhat tricky term, but almost all the time, you can just replace the word apparent weight with simply the normal force. You could just say, okay, forget the apparent weight. This is the normal force. I use symbol N. You could use symbol F sub N if you wish. Almost always, the normal force is what we're talking about when we're talking about apparent weight. That's how hard the seat on this person, how hard the seat's pushing up on them. That is what their apparent weight is. If they were sitting on a scale, that is what the scale would read. How hard the scale or the seat is pushing up on them. So let's again draw our free body diagram, this time of the person. So we've got the normal force pushing up that way. There's N. We've also got mg pulling down, mg. Now, if they're going to stay going in a circle, which one's got to be greater? Ask yourself that. If they're going to stay going in a circle, there must be a net force towards the center, so mg's got to be a little bit greater. I'm going to emphasize that by making this arrow a little bit greater. This has got a bigger radius, big R, so we're going to set up our Newton's second law equation very, very similarly. We just have net force C equals MAC, and in this situation, the net force, how are we going to put these in here? Well, we've got which one's positive? mg is going to be positive, mg, and in this situation, it's minus n, and I should clarify that this mg is I should connect it to the person, because that's the weight of the person that we're talking about. So, in fact, I'm going to go ahead and substitute in the capital M that we're using for the person's mass. So that's one of the forces. The other one is N, and it's going to be negative because it's pointing away from the center of the circle. mg minus N equals, and I'm just going to substitute, this is again the capital M, the mass of the person, and AC, I'll just go ahead and put in right now, V squared over, in this case, it is big R here. What's their apparent weight? Couldn't be simpler to solve for it. I'm just going to solve this very quickly, and you get, when you're all done, mg minus V squared over R equals N. That is their apparent weight. So let's take a look at this and see how this behaves as this thing gets faster and faster and faster. As the speed goes up, the normal force keeps going down and down and down. So that's why if you're going too fast, you might actually feel yourself lifted out of the seat, because the normal force, you'll be totally weightless when the normal force is 0, or you'll feel weightless. So those are some example problems, and hopefully that'll get you started at least, and that should take care of us for circular motion, at least for now. All right, we'll see you next time.